So good afternoon, everyone. Welcome back to Digital Control. The lecture that I will be covering for today is Z transform. Before you have seen Laplace transform, and you already know the advantage of Laplace transform. I will recall a little bit about Laplace transform. So if you have a continuous system represented by dynamic equation in the form of ordinary differential equation, you can transform it into Laplace domain so that you can make analysis. You can also manipulate the interconnected system, several systems together, and then you can do the inverse Laplace transform to get the solution in the time domain. And now you will see Z transform. A similar idea actually. It is used to it is a way to solve different equations. So if you have, let's say you have a dynamic equation in the form of different equations, as you can see here, hk minus 1, hk minus 2 represent the kind of series. So h can be, in this case, h is scalar, and you have equation that has a relationship between the sequence and the past sequence, right? So if you find, let's say, hk equal to something, it means you have the current value in function of previous value, okay, at different sequence k, and u is input. In some case, you may also have dynamic equation that depend on the current input and the previous input, okay? Like uk minus 1, like this. Once you have such kind of equation, you can do the Z transform into a complex domain or Z domain, and it has the form of polynomial on numerator and denominator. So you have a rational function, and again Z can be complex number. So from here, let's say you have you can transform the input into Z transform as well, and then you can manipulate it into a canonical form like this, and then you can find the inverse of Z transform to get the solution of H in the K domain. Actually, K represents time as well, okay? So actually, how do we get a different equation in terms of K, let's say? So most of dynamical system can be represented in the form of ordinary differential equation, okay? The differential is with respect to time. From, for example, RC circuit, LRC circuit, DC motor, pendulum, drone, almost all kind of dynamic system can be represented by ordinary differential equation, or a set of system of ordinary differential equation. It can be linear or non-linear, but anyway, for Laplace transform and Z transform, we apply for linear system only. Okay, but here, if most of equation are represented in the continuous time in the form of ordinary differential equation, then how you can get a different equations? In here you see, when you want to make algorithm to solve equations, solve differential equation, you need to use computer that work on discrete time. It cannot work in continuous time. So one way to use Euler method to approximate the continuous time equation into a discrete time equation. So here, let's see, you choose sample time Ts. Here, sometime some writer denoted delta T. And usually it should be small enough for a particular equation. And then Euler approximation is given by this equation. Okay, approximate the time derivative by this term, the term that so the derivative, which is the tangent line here, the black one, is approximated by the blue line here. So you need to know the current value at k and the previous value at k minus 1. Like here, delta h, right? So delta h divided by delta t is approximated to be the derivative h dot. Then you substitute the approximated derivative by the different, here the different formulation, into the differential equation. So the term derivative disappear. Then you only have different equation. Okay? Hk in terms of hk minus 1 and so on. In some case, you might automatically have the dynamic equation in the form of different equations, like the Markov equation for population growth by over the year. Okay, so it's formulated with the index k representing the time of the year, something like that. People move from one city to another city by the probability weight, so you can immediately get different equation, right? And here you get different equation from approximating continuous equation. And the next you see here is the definition of Z transform. And so when you have h in function of index k, right, then you can transform it into Z transform, Z domain, denoted by capital H of Z here, or Z transform of hk here. And the definition is the sum over the k from 0 to infinity of the value h evaluated at the time k. So k take from 0 to infinity, hk here, and time h to the minus k. So this is called a unilateral formulation. For the bilateral formulation, k taken from minus infinity to infinity. Okay. But if you want just use the notation with unilateral, then you just put additional assumptions that h at the index of negative number are all 0, right? Like this. Yeah, it looked complicated, but if you are still familiar, still remember the geometric series, the expansion, and then you can find a condition that make the series converge, so it's not too complicated. Like here, well, we have a notation of h of k or hk like this, and z can be complex number, and its absolute value must be within a range that guarantee the bound of the series expansion. Okay. So R0, lowercase r0 and capital R0 are the rank for value, the absolute value of Z that guarantee the series converge. Okay, the guarantee conversion of this series. And now let's apply the definition of Z transform into parse function, unit parse function here. Unit parse function is the delta of k equal to 1 if k equal to 0. Otherwise, delta of k is 0. Okay? And delta of k minus p. So this function equal to 1 if the inside argument is 0. If inside is 0, this function is 1. Okay? So that's why in here you can see that it equal to 1 when k equal to p. Same as this one, right? The argument inside is 0, then the function is 1. Otherwise, the function is 0. So the Z transform of unit parse functions can be calculated like this: Z of delta of k minus p equal to some measure of this delta function times Z to the minus k here, because this delta is 1 when k equal to p only. So you substitute k by p, then you just get Z to the minus p. Okay, this is transform of delta function with the argument k minus p. In one particular case, p equal to 1, then Z transform of unit parse function of this equal to just 1 over Z. 1 over Z is called unit delay. Okay. This is how you interpret the Z transform as a transfer function. Okay. You have Z of k here, and then you have unit delay here. Then the output is the memory at the previous time step or the previous index k. Something like this. Okay. How about Z transform of unit step function? You got the U step here. So unit step looks like this, right? So you have like index k like this. Zero here, and then get 1 here, 1 here, 1 here, like this. So here k equal to 1, 2, 3 until like at a certain value of k. This is unit step. Then you apply Z transform of unit step function by summation of k taken from 0 to infinity, and u is always 1 because k is from 0, right? And Z to the minus k. And how do we get this value? 1 over 1 minus Z to the minus 1. Now this series converges to a certain value if the norm of the Z not norm of z, but norm of z to the minus 1, right? Norm of z to the minus 1 of which is less than 1, right? And next the z transform for different equation. Let's say you have a sequence h of k minus p, and again with this condition, so that you can apply the definition of unilateral formulation. You apply z transform to this sequence, okay, and then just use the method of change variable by this k minus p by n. So it means this is n. It means k equal to p plus n. Okay? P plus n here, substituted into k here. And then you can take out the z to the minus p from here to be here for all the term. Then you have z to the minus p times z transform of h of k, right? Actually, you have seen that the z to minus 1 is unit delay. So z to the minus p is kind of delay of p time. Delay of p time, right? If you compare to here, z to the minus 1 means unit delay. And here you have z to minus p, then it is p time delay. Okay. So it's very convenient, right? When you transform h at sequence k minus p, then you just get z to the minus p times z transform of h of k. This is the way that you can transform different equation to be polynomial. No, I mean you are to find transfer function. Transfer function would be rational function where both numerator and denominator are polynomial. And here let's see one example. Z transform of h of k equal to 0.5 to the k times step function uk. This means hk is to be like defined to be like this: 1 and then 1/2. Oh, no, sorry, 0.5, 0.5 square, and so on, right? And now let's try to find the z transform of this series. So you apply z transform directly into this term, right? To this term. So you get here like this, and then you rewrite it in this form. This is geometric series expansion again, and with a certain value of z, you get this series converge, and you get the final compact form like this, right? Actually, this is supposed to be 1 minus 0.5 z power, let's call infinity as n. It's power n, maybe n plus 1. If we start from, because I don't need to write the 0 at 0, right? I don't need to write it, because at 0 k equal to 0, everything power 0 equal to 1, right? So I can write like this. Okay? And for certain value of z, this just convert to 0. That's why you only have 1 over this term. And now let's look example number 2. Actually, number 2 and number 1 is the same. Are the same. Example 1 and example 2 are the same. but I write it in different way. This one, you have the function h of k in terms of k directly, but this one you have like a different equation, right? This one is different equation, and let's test with some value k, then to see whether this and this are the same. When k equal to 0, when this is 0, then this one is 1, right? When k is 0, this one is h minus 1. H minus 1 is 0 here. So you have h of h1 equal to what? K equal to 0. 1. Let me see. Okay, right. Because this term is 0, right? So 0 times 0.5 is still 0. So it means you have h1 equal to 1. h1 equal to 1 is same as... sorry, this is h0, right? Sorry, h0. Because k equal to 0 here.
I just have a question. What is delta k is equal to what?
Delta k is unit pulse.
Is equal to this?
No, unit pulse. It is 1 when the inside argument is 0. Yeah, when inside here is 0, this delta function equal to 1.
Okay.
Otherwise, always 0. Okay. So, yeah, maybe it's better to look at the graph. This is k, and this is delta of k. And then delta of k equal to 1 when k is 0 here. And k equal to 1 here, 2 here, it's always 0. And even other when k minus 1 or minus 2, also 0 like this. So it's 1 only here. But for delta delta of k minus 2, for example, so it 1 here. This is delta k minus 2, right? Yeah. It should be here. Okay. And let's verify if k equal to 1, then you have h1 here equal to, yeah, so here h1 and here 0.5 times h0, which is 1, equal to, what about this one? This one is 0, right? So you have h1 equal to 0.5. When you substitute k equals 0 here, you get 1. And k0 here, you have h of minus 1. H of minus 1 is 0. So here is just 0. So it means h0 equal 1. Okay? h0 equal 1. From the previous value of k. And we do it repeatedly by increasing the value of k by 1. So h1 equal to 0.5 of, I can still put h0 here if you like, and then h2 minus 0.5 of h1 equal to 0, because this one always 0, right? Except when k equal to 0, and so on. So you can clearly see that hn plus 1, you can just write hn equal to 0.5 hn minus 1, right? It's geometric series. It must have finally have answer like this, right? So it's just that this is the way we write it in the form of different equation. And but you need remember that in the form of different equation you always need input like this.
So
Like
does it mean that they will have the same result, for example?
the same?
The same pattern?
Yes.
Yeah.
Yes, same pattern.
Just a different way.
Just a different form, right? This one is called explicit formulation. This one is implicit in terms of different equation. Then we can have a way like using Z transform to solve this equation. Not yet, sorry. But for now, I just check that this example and this example are the same. So what I was doing here, we can be said that this is a solution already. So different equation is the solution, but solution by numerical computation, different from differential equation. Differential equation you need to solve it, but different equation, the equation itself is the solution. But this solution needs to be computed by computer if you want to compute up to like large number of sequence. So the process here is the way to compute sequentially. But we also have another way to solve it by using Z transform. Actually, first we can apply Z transform both sides on this equation, and Z transform of part is always 1 unit parts, and Z transform of different equation HK like this. You can have Z transform of HK, and here you can have Z transform of this one. You can have 0.5 Z to the -1 and Z transform of HK, because Z -1 here represent the delay. So here is like delay or memory at the previous timestamp, previous K. Then finally you get Z transform of H of K to be in terms of this. And if you compare this one and this one, you can see that it's just the same, right? So the method, theoretically, you can have the formulation to apply to the Z inverse. Yeah, there is a formulation applied to Z inverse, and then you get the formulation or the solution in the K domain. Okay. Or you can use another method, which is first you have K domain and you transform it into K domain, and then you remember the form, right? And then if you want to solve different equation, you transform the different equation into Z domain, and then you do some manipulation on the polynomial, and you can make the canonical form that you can compare to the table. Then you can immediately use like a lookup table as a Z inverse. Don't need to apply formulation of Z inverse, but theoretically there exists formulation of Z inverse. It's like Cauchy integral or something like that. Yeah, it's very complicated. And so here is the illustration graphically in the form of graphic for the series, for this series. I often meet this problem. If I use this, I don't know today what happened to my PC. it's gonna restart. Okay, so here is the summary of the Z transform that you just saw earlier, so I don't need to repeat it, you can read it by yourself. And here is a table of Z transform for some special function, and I can say it again. For unit part, the Z transform is just 1, and step function Z transform is like this, or sometimes you can write it like this: 1 over 1 minus Z to minus 1. You divide it numerator and denominator by Z. And for RAM in the time domain T, like this. Yeah, RAM you have a curve to be like this, right? Okay, it's 45 degrees, right? Yeah, 45 degrees if the scale is the same, this time and this function. I forgot to explain it clearly that here you have a time domain, continuous time, and if you do Laplace transform you get this to this side. This is Laplace transform, but if you do the Z transform you get this. But before you apply Z transform you need to choose sample time. T can be substituted by KT, okay, capital lowercase t is K time T. T means simple time. Let me illustrate this function. Let me draw it again for the RAM, like this. And here is T, but if you choose a particular sample time like T here and then 2T here, so Z transform of this function, this discrete function, like this. Yeah, like this. In continuous time you have like this. It means for continuous time you can pick any value of T, right? This T can be any value, you pick it and then you can compute it, you can compute the function. But for discrete you can pick K, you cannot pick T, but you can pick K. Capital T is selected already, and then you pick the value of K. I mean this, you want the sample at this time, you want the sample at this time, and so on, like that. You cannot have the value at the 3.5 of T, like that. You don't have access to that. Okay, and so this column show the Z transform of this function. Okay, after you select sample time capital T, that's why you can see T appear here. Here are all some special functions like T squared, T to the n, exponential of AT, and so on and so forth, right? And if you look at on the right hand side, on this column, you can see the always you have polynomial function both on numerator and denominator. Like the exponential term e to the minus a times capital T, it's just some number because T is selected, the T, capital T is chosen to be some value, a is just some constant of the system, right? So here you have polynomial of z. And for trigonometric function in the continuous time like this, Laplace transform to be like this, and here is the z transform. Okay. And here I want to give one idea, I mean one awareness, not idea but awareness. When I ask how do we get a different equation, so one way is to approximate continuous system, a continuous equation from ordinary differential equation, right? Like here you have a differential equation, the solution to be, the continuous solution to be like this. Then you approximate, right? You just approximate to be these equations. So the term approximate means the solution from here must not be the same as here. Just close, can be close. Can be close or can be far, maybe. It depends on how you approximate it. For example, in here, if you choose TS to be 0.4 from here to here is from here to here 0.4 second. You can see the difference between these two curves, where the blue one is the analytical solution, this one, the true solution, okay? The analytical solution, and this is the solution from the approximate equation, right? Solution from approximate equation, it means the solution of this equation, which is this. So you can see that this function is not the same. These two functions are not the same, right? This is like e to the minus 2t, and here you have r to the k. K is 1, 2, 3, 4, 5 like that, right? And r is defined by this. But if you take limit of Ts approach to 0, this function will become this function. You can try at home by yourself. Okay? This implies that the smaller the sample time t, the better the approximation is. For example, here you can see the sample time is 0.1 second. It means in between this sample time you divide into smaller sample time, like 4 times smaller. Then you have the approximate solution closer to the analytical solution, like this. So this is awareness for you to know. But then let me ask you, when you apply z transform into a function, like for example t like this, is this a kind of approximation? I mean, if I draw the function of t, will it be just approximate, just close like this, or it will pass on the sample like this? Which one you choose? 1 or 2? When we apply z transform to the function, so you choose number 1. No, actually number 2. So this z transform apply to the actual function, continuous function, after you discretize, actually it does not lose any information. I mean, it's not a kind of approximate. It's just that you cannot access the value in between like this. But the value that you got here is the same as the one on the continuous.
So it will always pass by the points?
Because always.
The value between the points are not necessarily true.
Yeah, if you transform it from the actual function like this, it always passes the value. Okay? Be careful, you need to be aware. Because if you use the inverse Laplace transform of this one, inverse Laplace transform is one, you will get kt like this. And this kt, is it the same as t when you choose? Is it the same? Yes, it is. The only the difference is that you cannot access to the function in between the sample time. Okay? So must be aware of this. Not two things, I just give you two things. One is if you have continuous and then you approximate it to be different equation, of course here you got some error. Okay? Yeah. But if you apply Z transform to the function, the solution itself, you don't have any error. It's not an approximation. It just transforms to a different domain. And also, when you apply Z transform into different equation, let's say different equation is if you have a way to discretize the system that is not kind of approximation. You got what I mean? If you can do that, then you apply the analysis of Z transform. You don't get any error actually. It's just the value that you can evaluate is at the sample time with in sequential. So not this one, huh? This one. Before I move to the next point, you can have a break about 5 minutes, so we can return at 15 past 4.